First, I'd like to thank Professor Ogawa for his invitation. Give me a chance to have a talk here. Today, I want to talk about the Navier-Stokes equation in supercritical spaces. This work is a joint work with Professors Feichtinger, Gröchenig and Dr. Kuijie Li. First, I want to talk what we want to do. We consider the Navier-Stokes equation with the initial date in a class of modulation spaces, ESPQ. This ESPQ has a exponential decay weight. The weight, like here, this here is the norm in ESPQ defined in this way. We first put the characteristic function with center at the unit k plus 0 to 1 to d. Put the characteristic function between a Fourier transform and the inverse Fourier transform. Then act on f, then take a spatial RP norm, then have a weight to 2 to s absolute kq. Look at if s less than 0, these are fast decay functions when s less than 0. So you note here the frequency is localized in the k. Here is a 2 to s absolute k. So compare with here, the center is k, and this is the exponential decay functions. After taking RP norm, then it becomes a sequence of k. Then we take summation of the k to cd. Then d is spatial dimensions. These function spaces is a very rough function spaces. In fact, if we consider simple case such as p equal to 2 and q equal to 1, then we have any subleved spaces H sigma is a subspaces of ES1. This is for any sigma less than 0 and S less than 0. We mainly work on Navier-Stokes equation in these spaces, ES21 and its generalization ESR1 cases. We show that Navier-Stokes equation has a unique mirrored solutions in such kind of spaces. In these spaces, we will have further condition is we assume the initial date is Fourier transform is supported in RD1 cases, which means that RD1 equal to Xi belong to RD, every coordinate larger than or equal to 0. This is our goals. First, I want to emphasize some notations. The first notation is RP spaces. RP spaces, we simply write the norm is as we add a sub p, like denote RP norm. And subleved spaces HS norm in a standard way. I will take a Fourier transform, then times the weight, Japanese bracket 2 to s. There is a homogeneous variance f dot s equal to absolute Xi to s f Fourier transform take R to norm. This standard norm is standard notation f the Fourier transform of f, inverse Fourier transform. We use s denote the Schwarz spaces, s prime denote the dual spaces of s. There's a constant capital C larger than 1 and small c, small number less than c. The general constant can be different at different places. Now we consider the Navier-Stokes equation. We mainly consider the initial variable problem. ut minus Laplace u plus u dot nabla u plus nabla p equals 0. Dividend u equals 0. U0 is the initial date. Here we assume the spatial dimension is d. U0 is the initial date. P and U are known functions. Of course, U0 should satisfy the dividend U0 equals 0. First, I want to talk about the critical spaces. For Navier-Stokes equation, we have some scaling invariance in the sense that we take a lambda larger than 0. We take a u lambda of tx equal to lambda u of lambda square t lambda x. P lambda of tx equal to lambda square p of lambda square t and lambda x. If u is a solution, then we see that u lambda is also a solution for Navier-Stokes equation. But the initial data should be taken this way: lambda u0, lambda dot. Just we take here, we take t equal to 0, then u lambda 0, just this one, lambda u0, lambda dot. So according to the scaling invariance of Navier-Stokes equation, we can define the critical spaces, which means that we say that a function space x is a critical spaces if u lambda is invariant in x. Rough speaking, we take this u lambda t dot take x norm equivalent to u t dot take x norm. This equivalent has nothing to do with t and lambda. We know that h dot d over 2 minus 1 and LD base of spaces b dot minus 1 plus d over p, pq, and bmo minus 1 are all these functions are all critical spaces. In critical spaces, and we have some result on the global wire-posedness with small data. Kanden and Planchen and Sherman in base of spaces, they consider 3D cases. They assume that initial data is in b dot 3 over p minus 1 pq. In these cases, they show that Navier-Stokes equation is global wire-posed with small data. Then Kalk and Tadalo consider cases initial data in the BMO minus 1. And Iwabuchi, he showed that in modulation spaces, M minus 1 P1. Also, there were some regulatory criterions. The earlier version is when U belong to R theta T, RPX, theta P might satisfy these conditions. If U belong to these spaces, then U is a smooth solutions. Then this version was generalized by Kozuno, Ogawa, and Taniguchi. They consider the solution in the bigger base of spaces, which means that if U belong to such kind of spaces, R2, 0T, B dot 0, infinity, 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 then the solution U is smooth. And then Zhang and Yang, they developed the cases. They developed these cases into more general cases. He needed this condition, nebula times U belong to R2 over 2 minus R. B dot B here is a minus R infinity infinity. If U satisfies this condition, the solution also smooth. Also, there are some ill-posed result in critical spaces. Rough speaking, that is when since this spaces is critical, D dot minus 1 plus D over P. The ill-posed means that if P equal to infinity, P equal to infinity, this critical becomes B dot minus 1 infinity Q. So the ill-posed means that in all such kinds of spaces, when P equal to infinity, the solution map is discontinuous. Also, there are some global weak solutions in supercritical spaces. The collective result is due to Larry about 80 years ago. They show Navier-Stokes equation has a global weak solutions in R2 spaces. For Navier-Stokes equation, we have only such kind of result. We have no more result. If you consider the random data, we will have some super critical cases. Nakamura, Kuijie, and Stabilities, they show that random data in HS is S larger than -1/2. In these cases, they show that the global weak solutions. So in the supercritical cases, we all know the global weak result of weak solutions. Up to now, the uniqueness is still open. In this talk, we mainly consider class of supercritical data and show that Navier-Stokes equation is a global airport in a supercritical modulation species. Now, let me record the notion of modulation species. Modulation species is related to the frequency uniform decompositions. First, we record the definition of frequency uniform decompositions. We assume sigma is a smooth function, its support is included in these intervals -3/2/4, 3/4 to d, which means that the support sigma is compact. And the sigma k is a translation of sigma. We further assume that sigma k takes summation about k belong to ZD equal to 1. Then we can define the frequency uniform decomposition operators. Box k equal to inverse Fourier transform sigma k Fourier transform. You should note that sigma k is only a translation of sigma, which means that the structure of sigma k is almost the same as sigma. The only difference is that sigma k, sigma has a center at 0. Sigma k has a center at support center is k. So this box k almost has the same property as box 0. The modulation species was introduced by Feichtinger in 1983. Its norm can be equivalent defined in these variants. I've taken the modulation space norm, MSPQ equal to box KF, take RP norm, then times the Japanese bracket SQ, these reactive quantities, then take sequence RQ norm, then formulate the modulation space norm. You note here, this is you note that sigma k is the support of sigma k is supported a cube with center at k. So this k match with this k to s, which means that the frequency space is located in unit ball with center at k. So the reactive quantity is just k to s. This is quite different from originally I introduced here. This is the frequency space is k. This reactive quantity is 2 to s absolute k. This is exponential functions. This is the power functions. Now we can apply the frequency uniform decomposition. We can define the rather rough modulation space in this way, like 2 to sk times box kf take RP norm, then take a sequence RQ norm. In the case of s less than 0, ESPQ is a rather weak function species. To understand the ESPQ, we consider simple case as p equal to q equal to 2. In these cases, we have a simple version of ES22. It's just equivalent to this norm, 2 to s absolute cosine. I have to take a Fourier transform, then take a R2 norm. this is quite easy. Just here take 2, here take 2, then take you note that use Planck identity. The inverse Fourier transform disappears. When sigma k take summation is just equal to 1. So in this case, you easily find that FES22 norm is just equivalent to this variance. If you compare with this number, 2 to this weight, 2 to S absolute k, with the weight in subleft species, absolute Kuijie S, compare this with this one. With this one or this one, you immediately find that here in subleft species there is a power functions. They are also power function, but in this variance, this is the exponential variance. So we just observe this is equivalent to norms. You find that FES22 is here is a exponential weight. Here is a power function weight. So if S less than 0, you find that this function is decaying faster than any power functions, which means that this function 2 to S absolute k is less than Kuijie to S tilde. So this one is when S less than 0, this weight is less than this weight. So we immediately have that H minus n is a subspace ES22. This is for any n larger than 0 and S less than 0. This variance shows that when S less than 0, this modulation space is rough than any subleft spaces when this minus n is a negative index. So we usually get that using this equivalent norm, we can easily find that if we take a Dirac mirror take any order of derivatives, then this implies the f hat equal to c Kuijie alpha. So this function can be absorbed by this function. So we will have f belong to ES22. We can also observe that if f take Fourier transform equal to 2 to minus s absolute s over 2, these are the exponential growth functions when s less than 0. These are exponential growth functions. So note that this one can also absorb this one. So that kind of f also belongs to ES22. We can also consider a more complicated variance like this one. This is a series variance. We can Dirac mirror take m order derivatives in the direction xj, then take a series. We easily find that f take a Fourier transform. It's just equal to lambda to m over m factorial. Then they take a Fourier transform just equal to Kuijie to m. Then it's just equal to e to lambda e Kuijie. This function, of course, also can be absorbed by this 2 to s absolute Kuijie. So in this way, we can see that the function spaces like this or this one are very rough function spaces. We have some more problem if we directly define these spaces. Now we didn't say what f is taken from. If we recall that original modulation spaces, this variance we take is the subspaces of the dual spaces of Schwarz function spaces. Namely, we assume that f is a tempered functions. But in these spaces, in this spaces, you will take f as a template function spaces, we have some problems. The main reason is that the completeness will be lost. We can easily have an example like this. I'm take a Fourier transform equal to total absolute s psi over 2, then take a sigma psi over m. Such kind of Fm belong to ESPQ, but Fm has no limit in these spaces, in the dual spaces or Schwarz function spaces. So our idea is just result to get from the Shilov spaces as test functions. We assume we construct in Garfunkel Shilov spaces, they construct the p lambda 1 and q lambda 1 as a test of sim-norm. They assume that both f and f will take Fourier transform exponential decay functions. In this way, both f and f Fourier transform has a very rapid decay when x tends to infinity. In such kind of function is since such kind of function is exponential decay functions, so is in its dual spaces, we can contain much more functions than the dual spaces of Schwarz function spaces. So we denote by S1 the set of all infinite functions such as p lambda 1 and q lambda 1 be finite. S1 equal with the system of sim-norms p lambda 1 and q lambda 1 is a complete local convex topological spaces, which is said to be Garfunkel Shilov spaces. The dual spaces of S1 is written as S prime 1. We just use S prime 1 as a mother spaces of ESPQ. So using these spaces, we can overcome the difficulty for such kind of function has no limit. So we can treat that, we just treat the ESPQ as subspaces for S prime 1. The second question is S1 contain no smooth functions with compact support. The main reason is that if we take both k equal to inverse Fourier transform sigma k convolute with f, this is a problematic in S1. So to overcome this difficulty, we define such kind of spaces ESPQ. We assume that there exists fk belong to Rp Rd, support f of k take Fourier transform is contain these cubes, and f equal to the summation of all fk in S1 prime, and this function sequence 2 to S absolute k fk take a sequence norm first in Rp, then take a sequence Rq norm less than infinity. Then we take a ESPQ norm, it's just the infimum of such kind of all of possible decompositions of f. Then we can show that ESPQ is a Banach spaces. These are in the cases s less than 0. When s larger than 0, since this function space is very nice, so well, has much more regularities than usual Schwarz spaces. So we don't need to assume that in S1 prime, we just consider that S prime is okay. So these is only the cases when S less than 0. Okay, after we define this ESPQ, we can show that this is the equivalent norm as we defined before. Before we defined this version is a equivalent norm. Equivalent norms. Okay, so from PDE point of view, this is very useful. Since this is difficult to use, we want to use these variants. So we can show basic inclusions like this. Base of space B minus n PQ is a subspaces with ES PQ. This is in the condition S less than 0, which means that this ES PQ is rougher than any base of spaces B minus N PQ. Whenever minus N is how negative this number is, then it's always a subspace of ES PQ. In the cases S less than 0. The known version of ESPQ, the earlier version is define ESPQ by short-time Fourier transforms. They define in this way: short-time Fourier transform like this: F act on M psi T x G. M psi is the modulation operators. Tx is the translation operators. This short-time Fourier transform times the weight total as absolute psi. First take a RP norm, then take a RQ norm. RP norm is about x. RQ norm is about psi. But there are no more result about these variants. We only have these notions. On the other hand, to study PDE problems, the short-time Fourier transform basically has no use in our works. So we mainly use this variant. Now we can state a result on Navier-Stokes equations. This is a rather rough state. Let D larger than or equal to 2, S less than 0, R is between 2 and D. Assume that U0 belongs to ES R1. Note R is between 2 and D. We assume that U take a Fourier transform is included in the first octant. Then we can find the S0 less than or equal to S, such that the Navier-Stokes equation has a unique Meyer solution. U belongs to C0 infinity e to S0 R1 intersect with R tilde gamma 0 infinity S0 P1. These are the working spaces. We can forget this first. The norm is also for constructed solutions. Or we can show that there exists a small constant such that the solution is a real analytic way T larger than S2 over C2. C, the small constant depend on U0 in the spaces as ESR1. In our result, ESR1 is a supercube spaces. The reason is that if you can use the embedding like this, B to minus N R infinity is a subspaces of ESR1. So if you recall that this is the critical spaces, B to minus 1 plus D over P PQ. So in this any basal spaces is a subspaces of this function spaces. So this when this regulatory index S less than this one, whenever N is B minus N, when N is belong to R is arbitrary, this space is a subspace of ESR1. So our result is a supercritical. This space is ESR1 is a supercritical spaces. For any S less than 0, we have also R2 is subspace of ES21. This is the inclusion we have indicated before. We have some examples. U0 take Fourier transform is a polynomial times this one. You all take such kind of things. U0 take Fourier transform the P psi 1 times 2 to minus S absolute psi over 2. With S less than 0, the minus S larger than 0. These are exponential growth functions. So this function is very rough. Absolute we need is supported in the should be in the first octant. So we should times the characteristic function on RD1 cases. This P psi is vector polynomial should satisfy the p xi times xi equals 0. This mainly want to say divergent u0 is equal to 0. In our result, we have no smallness assumption on initial date, which means that this u0 can be arbitrarily large in these spaces. Now we have some time. I want to indicate some crucial ideas how to prove the result. We know that if we want to solve Navier-Stokes equation or some other evolution equations in negative function, negative index sublevel spaces, the main difficulty is we have a big problem in nonlinear estimate in negative sublevel spaces. The difficulty is that we cannot make out any nonlinear estimate in BSPQ. But in these spaces, ESP1 cases, if S less than 0, this is available. If we assume that U hat and V hat, the support of U hat, V hat in the first octant, we just have such kind of a simple estimate. U, V, take estimate in ESP1. It can be controlled by the U take a norm in ESP1 times V take a ES norm in ESP1, which means that if when we consider function U hat and V hat supported in the first octant, then ESP1 is essential Banach algebra. But you can imagine that even we take base spaces, we have no such kind of properties. Even we assume that is supported in first octant. This is why we can make some things in such kind of spaces. The proof is the proof. We use some delicate frequency uniform decompositions, which means that we can first use the definition of ESP1 equals such kind of variance. Then we further decompose UV, U and V. Decompose U and V as the frequency uniform variance. After make such kind of decompositions, here is box K, here box K1, box K2. K1 and K2 has essential such kind of conditions, K minus K1 minus K2. Take infinity number less than or equal to 3. This is quite important since using this condition, we can directly drop the summation of the K. So we can make a nonlinear estimate in ESP1. But if we consider the real quantity 2 as absolute by K to Japanese bracket K to S, this inequality doesn't hold. So the nonlinear mapping estimate in classical modulation that doesn't work. Similarly, in Basel spaces, since it's an essential such power function, so we can also not make such kind of things. So using this fact, we can directly change S2 to absolute K into S absolute K1 plus S absolute K2, since K1 and K2 has the same symbols. This idea is quite important in making to carry out solutions in such kind of spaces. They mainly imply that in such kind of spaces, ESP1, we can make some nonlinear estimate. But if we consider Basel spaces, we cannot. You must ask why we consider the function is flat transform was supported in one octant. The main reason is quite simple, also very simple. We just take a U and we take such kind of variance. This means that U is supported in U, the Fourier transform U is supported in sigma k, and V is supported. The Fourier transform V is supported in the cube as with center at minus k. So if k is large, k tends to infinity, we directly know that such kind of knob directly tends to infinity. But if we take a U height convolute with V height, is absolute the Z cube 0 to 2 to D, then U and V take such kind of equivalent to 1. So if we remove the condition of the support in the first octant, then this has been 1. This tends to infinity. This tends to 0. So this is not true. The reason that why we can remove the smallness of the initial data. The main reason that if we observe L2 cases, you find that this initial data. If U0 lambda take scaling, it's just equal to lambda to 1 minus d over 2, U0 to 2. You note that 1 minus d over 2, when say d larger than equal to 3, then this is should be very small when lambda is quite large. So this is we can direct in L2 cases we can direct change the large data U0 take 2. This is quite large. Then times this one is can be very small. This is the initial idea about L2. In this spaces, the scaling is not so easy, but we can also have such kind of things. This is U lambda 0, U0 lambda. U0 lambda take ESPQ now is less than equal to lambda 1 minus d over p times the U0 take the norm in ESPQ, which means that the lambda to 1 minus d over p can be very small. Even this quantity is quite large. So we can directly change the large data to a small data by scaling argument. The last step is we can make a small data global solutions by directly consider such kind of things. This step is a bit of standard after we know the previous 2 steps. Okay, this is my talk. Thank you.